Here's a video to help with the combined gas law. The combined gas law helps to track how pressure, volume, and temperature respond to each other as they change. Now first, let's try to get a conceptual grasp of what this is saying by focusing on just one side, and let's look especially at first at the top, P1 times V1. Now that equation is saying that P1 times V1 is going to be a constant. Now if that's true, when one of these goes up, the other has to go down. So if the pressure goes up, the volume goes down. If the pressure goes down, the volume goes up. And that's what you can see happening here. We have this balloon in a container where we've sucked all the gas out, so there's no pressure in that container. We've made the pressure go really down, and so you can see the volume is going up. They're inversely related, pressure and volume. All right, let's focus on the pressure and temperature. What relationship do they have? Well, they are on opposite sides of a fraction. So if these are going to equal a constant, when pressure goes up, temperature goes up. And if pressure went down, temperature would go down. That's why space is so cold. There's so little pressure in the gases there. But if the pressure goes up, the temperature will go up. So here we have a piston, and there's a piece of cotton inside. Now, as somebody presses on this, the pressure inside of this piston gets bigger, bigger, bigger. As the pressure goes up, the temperature goes up. So much so, what happens to the cotton? It lights on fire. All right, how about volume and temperature? What's the relationship between those? Well, again, different sides of a fraction. So when one goes up, the other goes up. When one goes down, the other goes down. They're directly related. So here, if the temperature goes down, the volume should go down. We have liquid nitrogen, very, very cold. Put a balloon in that. What happens? Well, we're making the temperature go down, so the volume should also go down. Temperature and volume directly related. One goes down, the other goes down. One goes up, the other goes up. All right, so a question asking about these relationships might look something like this. It says a sample of oxygen, O2, at a gas at a pressure of 815 millimeters of mercury has a volume of 44.2 liters. If the temperature and amount of gas does not change, what is the final volume in liters of the gas at 2 atmospheres? Okay, so what I got from that was I have a lot of pressures, temperatures, and volumes. Now if you ever have more than one pressure, temperature, and volume, always use the combined gas law. P1 V1 over T1 equals P2 V2 over T2. Now we're going to separate that from our notes. Every time I have an equation, I like to write the variables separately so that as I go through the problem, I can organize any of the numbers I come across. Alright, so now we're ready to read the problem again. It says a sample of oxygen, O2, at a pressure of 815 millimeters of mercury, that is P1 right there, going to plug that in over there, has a volume of 44.2 liters, that's V1, I'll plug that in right there. If the temperature and amount of gas does not change, now, if something does not change, that means you can take it out of the equation. Now, nothing in the equation talks about the amount of gas, so we don't have to worry about that. But if the temperature doesn't change, well, we can cross that out, and we're left with this equation. And it says, what is the final volume in liters? So that's what they're asking for. They're looking for V2, specifically in liters. And then they say, of the gas at 2 atmospheres. That is our P2, so I'll plug that in there. Now, before you plug the numbers in, you want to check two things. First, do all the units match? And second, if you have temperature, is it in Kelvin? It has to be in Kelvin. Temperature is in the denominator. Kelvin is the only temperature scale where you wouldn't have a 0 there. Remember, you can't divide by 0. So, if you ever have a temperature, it has to be in Kelvin. Well, first, we don't have a temperature here, but do all the units match? We want the volume in liters. We have it in liters, so that's good. This pressure, P2, is in atmospheres. P1 is in millimeters of mercury. So we've got to convert between those two. The conversion factor that relates millimeters of mercury in atmospheres is there are 760 millimeters of mercury in 1 atmosphere. So I'm going to convert that top number, 815 millimeters of mercury. Every time you do a conversion, write a multiplication sign, a fraction bar. The units you start with always go on the bottom of that fraction, so they'll cancel out. I'm going to fill that fraction in with my conversion factor. So next to millimeters of mercury goes 760, going over the fraction bars like going across the equal sign. And on top you've got 1 atmosphere. Millimeters of mercury cancel out, and you're left with atmospheres. Now if you plug this in a calculator, if you put 815 times 1, enter, divided by 760, enter, should get 1.07 atmospheres. So now all our units match. We've got atmospheres and atmospheres, liters and liters, so we can plug this in our equation. Instead of P1, I'm going to write 1.07. Instead of V1, I'm going to write 44.2 equals, instead of P2, I'm going to write 2, and V2 is what we're looking for. On the left side, if you do 1.07 times 44.2, that should give you 47.294. And on the right side, we still have 2V. Now we want to get the V by itself. So right now it's being tied to the 2 through multiplication. So we do the opposite operation, division, with the same number, 2. Now if you do that to one side, you've got to do it to the other. It cancels on the right, and we're left with V2 equals, and plug into a calculator, 47.294 divided by 2 gives you 23.647 liters. That would be the volume. Now, does it make sense? Well, the pressure got bigger, went from 1.07 to 2. Pressure and volume are inversely related, so if the pressure got bigger, the volume should have gotten smaller. And it did. It went from 42.2 liters to 23.647 liters. All right, this question says, assume that V and N are held constant. If a tank of helium gas with an initial pressure of 0.786 atmospheres and a temperature of -22 degrees Celsius is heated until the pressure is 1,393 torr, what is the final temperature in degrees Celsius of the gas? Okay, so out of everything I just read, what I understood is there's more than one temperature, pressure, and volume. Got a lot of those. Anytime you have more than one temperature, pressure, or volume, you use the combined gas law. P1 V1 over T1 equals, yep, you guessed it, P2 V2 over T2. And I like to separate that from our work. We're going to write each variable separately, so as we read through the problem, we can organize the numbers we come across. All right, now we're ready to read through the problem. It says, assume that V and N are held constant. Held constant! That means we can cross them out. Now, there's no N here, but we do have V. So let's cross that out, and we're left with this equation. If a tank of helium gas with an initial pressure of 0.786 atmospheres, so that's clearly P1. There we go. Plug it in there. And temperature of -22 degrees Celsius, that is T1, so I'll write that over there, is heated until the pressure, this is the second pressure is 1,393 torr. I'm going to plug that in for P2 down there. What is the final temperature? So that's what they're looking for. T2 in degrees Celsius. So that's T2. I'm going to write question mark degrees Celsius over by T2 of the gas. All right, so this is what we've got. Now, before we plug numbers in, we have to check two things. First, do all the units match? And second, if we have temperature, is it in Kelvin? It's got to be in Kelvin. Kelvin's the only one that won't be 0. We can't have a 0 at the bottom of a denominator. Well, the pressures don't match. We've got 0.786 atmospheres and 1,393 torr. So we're going to have to do a conversion. And the conversion factor between atmospheres and torrs is there are 760 torr equals 1 atmosphere. A torr is the same thing as millimeters of mercury, so it's really the same conversion factor. 760 torr equals 1 atmosphere. So I'm gonna convert P2 here. So I've got 1,396 torr. Every time you do a conversion, write a multiplication sign, fraction bar. Units you start with go on the bottom, so they'll cancel out. Then I'm gonna fill that fraction in with my conversion factor. Next to torr goes 760. Going over the fraction bar is like going across the equal sign, and on top, you've got 1 atmosphere. Torr cancels out, we're left with atmospheres, and if you plug this in a calculator, you do 1,393 times 1, enter, divided by 760, enter, you should get 1.8 atmospheres. Alright, so now the pressures match, the units match for pressures. Second thing we have to make sure is the temperature in Kelvin. Our temperature is in degrees Celsius, so we get to convert to Kelvin. Now remember, the equation for this is Kelvin is degrees Celsius plus 273.15. So we're going to take those degrees Celsius, add 273.15, that gives us 251.15 Kelvin. Alright, so those are our numbers. Now I know Kelvin here doesn't match degrees Celsius. What that means is, once we plug these in, we're going to get an answer for T2, but it's going to be in Kelvin, because that's what we plugged in. And we'll have to convert back to Celsius once we have the number. Alright, so let's plug these numbers in. Instead of P1, I'm going to write 0.786. Instead of T1, I'm going to write 251.15 equals, instead of P2, I'm going to write 1.8 atmospheres. And I've got T2 on the bottom there. Now on the left side, 0.786 divided by 251.15 gives you 0.00313. And on the right side, we still have 1.8 divided by T2. Now what we want is T2 all by itself on the top of a fraction. So the first thing we have to do is get it to the top. The way we get it out of the bottom of that fraction is to do the opposite operation that's being done right now. This is division. We're going to do multiplication by T2. Now if you do that to one side, you've got to do it to the other. T2 cancels on the right, and we're left with T2 times 0.00313 equals 1.8. Alright, now we want T2 by itself, so we've got to get rid of this number. It's being tied by multiplication, so we're going to do the opposite operation, division, with the same number, 0.00313. You do that to one side, you've got to do it to the other. Cancels on the left, and on the right, 1.8 divided by 0.00313. That should give you T2 equals 575.1. But note, the units are Kelvin, right? We plugged Kelvin in for T1. So that's what we're going to get out for T2. But the question was asking for degrees Celsius for T2. So we're going to do a conversion. Now remember, Kelvin equals degrees Celsius plus 273.15. So instead of Kelvin, I'm going to write 575.1. That equals degrees Celsius plus 273.15. Now we're trying to get it degrees Celsius all by itself. So it's being tied to this number through addition. We're going to do the opposite operation, subtraction, with the same number. If we do it to one side, we've got to do it to the other. Cancels on the right. And we're left with 575.1 minus 273.15. That's 301.95 degrees Celsius. So that would be your final temperature. Now, does that make sense? Well, what happened to the pressure? The pressure went up. It went from 0.786 to 1.8. And pressure and temperature on opposite sides of a fraction are directly related. So, if the pressure goes up, the temperature should go up. And lo and behold, it did. Started at 251.15 Kelvin, sorry. It started at negative 22 degrees Celsius, and it ended at 301.95 degrees Celsius. So it went way up. And when the pressure went up, the temperature went up. Just like that cotton, which went on fire as the pressure went up when the piston went down. Alright, this question says a sample of argon gas has a pressure of 699 millimeters of mercury, a temperature of 30 degrees Celsius, and a volume of 4.48 liters. What is the final pressure of the gas in atmospheres if the volume contracts to 1,220 milliliters and the temperature rises to 341 Kelvin? Assume the amount of gas does not change. So that sounds like it's a crazy problem. What I got out of that is I have more than one pressure, temperature, and volume. If you ever have more than one temperature, pressure, or volume, you use the combined gas law. That's P1 V1 over T1 equals P2 V2 over T2. You separate that from your work where you write each variable separately so that as you read through the problem, you can organize the numbers you come across. Alright, we're ready to read through the problem again. It says a sample of argon gas has a pressure of 699 millimeters of mercury. That is P1. So I'm going to write it over here next to P1. A temperature of 30 degrees Celsius. It's the first temperature they're given, so that's T1. I'll write it over here by T1. And a volume of 4.48 liters. That is V1, so I'm going to write it over here next to V1. What is the final pressure of the gas? That's what they're asking for. They want to know what P2 is, and specifically in atmospheres. What is the final pressure of the gas in atmospheres? If the volume contracts to 1,220 milliliters. That is our V2. So I'm going to write that down here by V2, 1,220 milliliters. And the temperature rises to 341 Kelvin, so that's T2. So I'm going to write 341 Kelvin down here by T2. All right, so we have, and it says assume the amount of gas does not change, but the amount of gas isn't in this equation, so we don't have to worry about that. Now, before we plug these numbers in, we have to make sure of two things. First, do all the units match? And second, if we have temperature, is it in Kelvin? So, first pressure. Well, this pressure is in millimeters of mercury. We want it in atmospheres, so we're going to have to convert. The conversion factor between millimeters of mercury and atmospheres is, there are 760 millimeters of mercury in 1 atmosphere. So we can take this 699 millimeters of mercury. Every time you do a conversion, write a multiplication sign, a fraction bar. Those units you start with go on the bottom of the fraction so they cancel out. I'm going to fill that fraction in with our conversion factor. Next to millimeters of mercury goes 760. Going over the fraction bar is like going across the equal sign, and on top you've got 1 atmosphere. Millimeters of mercury cancel, you're left with atmospheres. When you plug this in a calculator, you'd have 699 times 1, enter, divided by 760, enter, you should get 0.92 atmospheres. So now the units for pressure match, so that's good. Next, volume. V1 is in liters, V2 is in milliliters. Have to do a conversion there. Now the conversion factor to go between milliliters and liters is, there's 1 liter equals 1,000 milliliters. So I'm going to convert milliliters down here. So 1,220 milliliters. Every time you do a conversion, you write a multiplication sign, a fraction bar. Those units you start with go on the bottom of the fraction so they cancel out. In this case, that's milliliters. And now I'm going to fill that fraction in with my conversion factor. Next to milliliters goes 1,000. Going over the fraction bars like going across the equal sign. And on top, you've got 1 liter. Milliliters cancel, we're left with liters, and if you plug this into a calculator, you've got 1,220 times 1, enter, divided by 1,000, enter, you should get 1.220 liters. All right. So, pressure units match, atmospheres, volume units match, liters and liters, temperature units, degrees Celsius and Kelvin. Which one should we convert to? Kelvin. Temperature always has to be in Kelvin, because that's the only one that won't give us a 0 in the denominator ever. So far, human beings have not observed absolute 0. So we have this degrees Celsius for T1. We're going to convert it to Kelvin using this equation. Kelvin equals degrees Celsius plus 273.15. So we'll take that degrees Celsius, add 273.15, and that will give us 303.15. Now we have units matching and in Kelvin for temperature. Alright, so now we can finally plug these numbers in. Instead of P1, I'm going to write 0.92 atmospheres here. Instead of V1, I'm going to write 4.48. Instead of T1, I'm going to write 303.15. On the other side, instead of P2, I'm going to write P2, because that's what we're solving for. And then for V2, I'm going to write 1.220. And then instead of T2, I'm going to write 341. All right, now, if you do the math on the left side, 0.92 times 4.48, enter, divided by 303.15, enter, that should give you 0.0136. That's that left side. On the right side, you'll still have P, but if you take 1.220 and divide it by 341, that'll give you 0.003578. Now we want to get P by itself. It's being tied to this other number through multiplication, so we're going to do the opposite operation, division, with the same number. If you do it to one side, you've got to do it to the other. Cancels on the right, and P2 equals 0.0136 divided by 0.003578. Plug that into a calculator, you should get 3.8. And the units, well, we plugged in atmospheres, we're going to get atmospheres out. Atmospheres. So, the P2 for this would be 3.8 atmospheres. That's the pressure that the gas would exert at that new volume and temperature. Thanks so much for your attention.